Okay, so let's get started. Progress check. So the most burning item is how is Bomb Lab going? Who's all done? Who's got all but the last part? Good, solid. So that's good progress. So other things that are ongoing, the quiz that's due next Wednesday has been out, so that's quiz 7. So we've got 4 weeks left, right? So the next 3 weeks, there will be just 2 more quizzes, quiz 7, quiz 8, in that time frame. Programming assignment 5 on caches and the memory hierarchy will be released really soon. And again, that's going to be roughly 2 weeks at least work time for you. And so just all the way to the end of the semester, 2 more programming assignments, 1 on caches, 1 on digital logic. Good. Okay, so in terms of getting what we need to learn out of your experience playing around inside the Bomb Lab, the next part that we need to explain is, so what's the deal about phase 5 and phase 6? What is the thing that you're supposed to observe being done in phase 5, phase 6? And that's all about how arrays and data structures such as linked lists are implemented at an assembly level, right? What does that look like when it gets compiled into assembly? Some quick recap of last Thursday's class. So Thursday we talked about how function calls are implemented at an assembly level. At the beginning of the class, we had this whole thing called the pointers lab, which we talked about how pass by value, pass by reference takes place, how the memory is divided into a heap section and a stack section, and how there's a discipline to how the stack is constructed, right? The shape of your function dictates what gets put on the function. And as you call functions, as you recurse, the function calls get piled onto the stack. So Thursday's class was all about that. The story of how to think about how function calls are supported. The story goes like this, right? There's 4 main things that has to take place. And then there's additional bookkeeping, additional kind of maintenance that you have to do. So the 4 main tasks is you have to be able to transfer control to the function. You have to be able to pass parameters to the function. And when you come back from the call, you have to know where to pick up, right? You have to know the return statement doesn't tell where to return to. So somewhere in the computer, somewhere in the memory, there has to be a record of where you should pick up. And then same thing, the data calculated by the function should be able to return. And then once you come back from your function call, your stack should be restored all to a sane state, right? It should be restored to the state that's expected before you prepared for the function call. So in Thursday's class, we did a pretty good and thorough job of inspecting the first 3 parts. I just wanted to come through this part of the slides again to recap and just kind of explain some things a little bit better. The important context, the important state inside the CPU here is there's a couple. One is the instruction pointer, which tells you what's the next assembly that's going to execute. The other is this other register value that's important called the stack pointer, which points at the top of the stack, right? The stack is a special organization of the memory, and there's one important memory address, the top of the stack, that's particularly important. It's so important that the CPU for x86 has a dedicated register just for storing where the stack is currently ended. So when we call into a function, right? So we can implement calling. So call, the assembly instruction call, what it will do is it will replace the instruction pointer with the destination function. Right? This is how how control is transferred to the called function. And as you call into the function, you're going to have a sequence, right? You're going to have a set of function call arguments to pass to the function. Most functions don't have that many arguments, so it's useful to support functions with relatively few parameters with speedy registers, right? Accessing registers is very fast. And so there's this standard called the application binary interface, which holds true for all programs running on x86. The standard here is as you call into a function, the registers, 6 of these registers will store the function arguments to the called function. And we see a very concrete example of this pretty much in every single phase of the BOM lab. Right? One of the useful tricks for BOM lab is if you wanted to know what's the format of the string you're supposed to provide to the phase, a very useful trick is the BOM will progress to a point where it's going to scanf, right? It's going to scan from the command line input from a string that you got from the command line, and it will try to parse that command line input. Right? And we've used scanf before in the programming assignments. The shape of it is it's got at least 2 function arguments. The first is the string to be parsed. So this would be an RDI. The second is the string's format, so the printf format that you would like to parse the string as. And so you can examine the register RSI, this will be the second argument here, inspect the memory location, and you would get what's the format that you're supposed to enter. Right? So if you didn't know, for example, that you had to have 6 numbers for some of the phases, you can come here and you would see it expects %d, 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 6% d's. That's the format of the string you're supposed to provide. So the BOM lab is very clever. Right? The BOM lab is designed to illustrate a lot of things. So any guesses why they chose to have 6 integers they ask you to input? What does that illustrate here? Yeah. Yeah, so if you didn't have that many integers you're expected to input, it would have all just taken place just using the registers. But because it's designed, it asks you to give it 6 integers. It forces that this scanf has a pretty long set of arguments. And so the additional 2, the final 2 integers, are going to have to be called into scanf using memory. Right? It runs out of the registers allocated to pass arguments, and the rest will be passed using stack discipline, right? Using special discipline on how the stack is supposed to be organized to pass parameters. Okay, so recap, right? Story so far. We've talked about passing control to function. We've talked about how to pass first 6 arguments to the function. So how exactly are those final 2 arguments passed? The standard here is that as you call into a function, as you're calling into a function, so say function P is about to call Q, or for example, in the BOM lab, the function called read 6 numbers is about to call scanf. The last 2 arguments to scanf have to be built up, right? It has to be built up in the current frame. You would start pushing values onto the stack to create argument 7 and argument 8, and then get ready to call Q, right? The destination function, the function to be called, in this case, scanf. So if you take a look at the assembly code, you'll see exactly this pattern going on. It will push onto the stack argument 7, push onto the stack argument 8, and then get ready to call Q. Good. And so this is the mechanism of those push and pop instructions. we can study this slide to see, okay, push is a kind of special instruction that has a neat side effect, right? At basic, push is really just in other words, what kind of instruction? Think to the quiz now. I believe quiz 6 did exercise something along these lines. If not, it'll be on quiz 7, so it'll explain what that question is. So I'm about to push a register value onto the stack. In other words, it's basically what? It's kind of like what other kind of instruction we've seen so far. You were about to give a guess? There. Yeah, go for it. An add function? Not quite, right? So think about it, right? Push. The task of the assembly instruction push is going to move a register value specified in source onto the stack. In other words, it's basically what kind of instruction? It's exactly a move instruction, right? You could take the push instruction and decompose it into a move instruction. It will move the source value to the memory, dereference the memory location, and what memory location is relevant here? What's the implied memory location? The top of the stack. Where is the top of the stack specified? How do we know where the top of the stack is? RSP, right? Exactly. So in other words, the push instruction, you can think of it as a move instruction from source register to the top of the stack, that location dereferenced. Now, it has also an additional side effect. What's the side effect? We just push something onto the top of the stack, and so the location of the top of the stack has changed. So what has to be updated? So I think you were close there, so what's the side effect?
So now RSP would have to be added to the amount of...
Yeah. RSP has to be appropriately, in this case, decremented. Now, that's a weird thing, right? The stack grew, but the stack grows downward into the addresses, and so the top of the stack decremented to indicate the stack has grown. Does that make sense? Did we see this in a quiz question already? No, right? So it's fine. It's going to be on quiz 7, right? There's going to be a question which basically asks you what two instructions are essentially equivalent to the push instruction, and now you'll get it, right? Same idea. Pop. What is pop equivalent to? Yeah.
So I'm guessing it kind of like sets the pointer value to like above the top, so I can see it on the right. It's kind of skipping over that top value. That's one of them, but I'm not sure about the other.
Okay. So we're okay with, let's pause there, right? So we're okay with what push was all about? Okay. Now, what's the semantic of pop then?
Also another move, because you're moving it out of the stack.
Good. So it's just like a move instruction, right? It's just like a move instruction. It's moving from a location in memory. What location? The top of the stack. And it's moving it to a register. So it's just reading out of the memory, putting into register. So in other words, pop can also be decomposed as a move instruction. And what's the side effect? Yeah.
Now you have to increase RSP.
Yeah, so you have to indicate that the stack has shrunk by the right amount. And to indicate that the stack shrunk, the top of the stack has moved up a little bit in address, and so it will increment RSP appropriately. This makes sense? Yeah, so why did I put this story here, right? Why did I talk about pushing and popping here? Well, so this is exactly how you build up the rest of the arguments for the called function, right? So once you're in the called function, you will access the first 6 arguments as expected in the register set, and the assembly code will also understand to get the additional arguments, if there are any, they will get them relative to the stack pointer. It knows to get the rest of the arguments, look relative to the stack pointer and a correct amount of addresses above the stack pointer, and you'll find argument 7, you'll find argument 8. Yeah?
So for pop, we usually return whatever we pop. So how does assembly handle that?
So it returns, so pop removes data from the stack, and it puts it into a register. Which register? That's an argument specified in dest. So if you look here, pop Q will store a value into RDX. So you see RDX goes from originally 0 to the value of 1, 2, 3. And where did this 1, 2, 3 come from? It came from the value that was at the top of the stack. Right, so 1, 2, 3 goes from top of the stack to RDX. Yeah. That's just how it's organized. So 7 to n, this is the convention. So let me be more correct, right? So let me be more correct on what I said when I explained. As P is about to call Q, it will start executing a sequence of push instructions. Correctly speaking, it will push argument 8 to scanf and then push argument 7 to scanf. I misspoke earlier, right? I got that sequence backward. I said 7 and then 8, but actually push 8, push 7, call Q, call scanf. Good. Okay, so story, right? So basically we now understand how data is passed to the function, and the function can do whatever it needs to do, right? It can be a loop, right? In several pieces of the bomb lab, what's going on inside the called function is some kind of loop or some kind of data structure traversal. It does what it needs to do. What has to happen when the function comes back is we need to know where to come back to. We need to know where to come back to. So this picture here is call and return, right? Call has a argument. So call will say call a function label. A function label is just a memory address indicating the beginning of the assembly code for the called function. And that, in other words, takes the value and puts it into RIP. Now, I'm going to say something a little bit interesting now, right? Quiz 7 has a question where it will demonstrate that you can take a push instruction and replace it with a move and an increment. And in fact, you can experiment, right? You can, if you want to have a hand at modifying assembly code, you could take some assembly code and find and replace some push instruction, replace them with move and increment decrement appropriately, and the assembly will still run correctly, right? They are semantically the same. I thought to do that about the call instruction, right? So I got clever, right? I thought, okay, well, maybe we can replace call instructions with a move, right? A move immediate value of this value into RIP. Now, why would that be the same? The claim here, right? Call is kind of like writing a value into RIP. Why do those mean the same thing? So what does it mean to call an instruction? Or call a function? Yeah.
It means you start running the code of that function.
And so what does it mean to start running the code of that function?
It means that you start with the beginning of the function in the instruction pointer and you continuously go ahead.
Yeah, right. The instruction pointer changes its value to the beginning of the function. So here, I'm going to call 400540. So RIP jumps in value from the original next instruction to 400540. Now I attempted to replace call instructions with move instructions, right? You could say, okay, I'm just gonna move 400540 into RIP. The computer does not like that. Like the program crashes. Right? It doesn't allow you to modify the RIP instruction in that way because that's quite dangerous, right? The RIP is a heavily guarded register that assembly cannot just arbitrarily read and write to. Using move instructions, you can only modify RIP using call and return. Just an interesting tidbit. Okay, so this is how we call functions, and how do we return, right? Return doesn't have a argument on where to return to, right? It's implied in the code structure, right? It will return to the calling function. How does the computer know where is the calling function? Well, back in this picture, it's the last thing that's recorded, right? So the structure of function call frames is the last thing pertaining to the calling function is the return address. That's kind of like this address is pushed onto the stack, and when you return, it's kind of like this value is popped off the stack and written into RIP. So just to tie things together again, right? If, just a pop quiz, right? If we wanted to get rid of the return instruction, what other instructions are kind of like return? Yeah.
Could we move back to the original location?
Good. So move, we can say let's move what value? The value at the top of the stack, right? The record of the return address. Move that value from RSP, dereferenced, and put it into RIP. Now you could try that. The computer does not like that, right? Like I said, the RIP is a heavily guarded register. You can't just write to it arbitrarily. You can only modify using call and return. But in essence, is exactly what's happening here. It's just taking the address to return to and moving it into RIP. What's the additional thing that has to be noted here? It has a side effect. What's the side effect? Yeah.
Have to reduce the RSP value because your stack has shrunk.
That's right? Just like the pop instruction before, return, popped the return address off of the stack has shrunk, and so RSP will increment a little bit, right? Just like indicated here, RSP increments a little bit to indicate that the stack has shrunk. Good, so storytelling, right? So far, we've explained how controls transferred back from the function. And so what we'll have to talk about next is how data comes back from the function, right? So this part here, how returns are taking place. So for this, there's two sets of slides I just want to refer to from the textbook slides. So this is about how data comes back to the caller, right? So the convention is the return value of a function comes back through the RAX register. And we can point this out in slides 33 through 38 of the textbook slides on procedures. So here we have their example of incrementing a function. This is implemented as you can see that this function is supposed to return x. So x is last stated to be just the dereferenced value from the first argument. And so right away here, increment already implements that semantic by dereferencing the first argument and putting that into the returned register, into RAX. And then you can trace through the rest of the slides. You can trace how RAX is used in this function, where this one now calls the increment function, right? So here's increment, here's call increment, and same thing, the RAX register stores the return value for call increment, right? And so this set of slides here just basically illustrates that walking through, right? And I can step through this slide by slide. It's a lot to study through, but the key kind of thing to note is exactly this, that RAX holds the return value. Right. So final piece of the story. So coming back to our storyline here, now that we've returned from our function, well, the calling function, right, the function that was called, can do all kinds of modifications to the register values. And when we come back to the function that called, the caller function had set up its stack and set up its register values to hold what it intended to, right? So there's also additional discipline in when you return from a function, the register values have to be restored appropriately. Otherwise, so think about this, right? A calling function, the function that's about to call Q, it has no understanding of what Q might do, right? Q could take all the registers and write them to 0, for example. And it's totally not what the calling function, the P function, expected. And so there has to be discipline between every function on how it's allowed to modify its registers, and if it modifies them, how does it restore them to their original value. So for this, we'll again quickly refer to the textbook slides, now 40 through 44. So for this, there's kind of this arcane knowledge on some of the registers are termed caller saved, some are termed callee saved. So caller save means that the callee function, P, or read 6 numbers, it's about to call scanf, right? And in preparation for calling scanf, it's going to save or protect the registers that read 6 numbers, the calling function cares about, and it will store them in the stack in preparation for calling. Callee saved, right, so the next category is some registers. If a function, its implementation will use some registers as scratchpad, it's the called function's responsibility to restore those register values before calling return. So the organization is like so. This slide here summarizes all the caller saved functions, caller save registers. So if read 6 values, I'm about to call scanf, and I care about these registers, then these register values have to be pushed onto the stack before calling, right? So let's tie this together, right? These are caller save registers. I am read 6 numbers. I'm about to call read 6 numbers, and so what do I have to do? It has to pass 6 arguments at least, right? And 6 of those arguments are these registers, RDI, RSI, RDX, 8 and 9. These are all caller saved, meaning that if I, read 6 numbers, care about these registers, it's my responsibility to save these values because they're going to be changed by the called function, scanf. Right? So if you study the assembly code for, say, read 6 numbers, you'll see this pattern of as it's about to call scanf, it will start pushing the register values, RDI, RSI, RDX, onto the stack to store them, and then modify the values of these registers to pass to scanf. Does that make sense? Yeah.
And so then after scanf is done, that's why there are a lot of pop statements after, because the caller frame is restoring the registers after it was used by the.
That's right. Right. So when we come back from scanf, we want to restore our context. Right? We want to restore our environment where what we wanted to have in our registers is what it was before. And so there will be a sequence of pop functions, pop instructions, taking what's on the stack, item by item, and restoring them into the register set. That's right. The other category here, again, arcane, on which ones are which ones are caller saved, which ones are callee saved. These other registers are callee saved, which means that if scanf, the called function, will take advantage of these registers, it's the called function's responsibility to restore them before calling return, right? Because the caller function might want them to be whatever the original values were. So good. You can see the example of this in the slides here. You can also see this in the bomb lab, this exact pattern of pushing register values and popping them off to restore the context. Okay, so that's basically how stack discipline is enforced, right? This whole picture of function calling and returning is created by this careful dance. And so kind of the end result is this elegant system, this elegant machine where recursion can happen naturally, right? So we can take a look at an example of this in an example code. So this is in the PA4 directory. There is a last example in the assembly procedures directory called 3 recursion. And 3 recursion is this function here, right? So what does this function do? Take a look at just these lines of codes, and what will this function do? This is very terse code, but stare at it a little bit and see what do you think it does. Yeah. Okay, it converts it into binary and return it recursively. Getting warmer. So let's use some more clues. I'll give you some more clues, right? So the comment here for 3 recursion is called recursive pop count. Where was pop count example? Nope. Nope. Where was the pop count example? I forget. Pop count was given as an example in some other part of this chapter, right? But the clue here says it's recursive pop count. So what this function does to spill the beans is it will count the number of ones in the binary representation. How does it do that? Yeah.
So basically, if it's like it goes like bit by bit from the left to the right.
Good.
And
So
it looks
pause
that
there,
way.
right? So that's the first part. It goes bit by bit from left to the right. Where do you see that implemented?
Because like in the return part, it's then bit shifting is adding a bit to the right, so therefore it has to, and that would essentially delete like the leftmost bit, so therefore it has to be looking at the leftmost bit and then like deleting it, or like turning it into, or like pushing like the way back.
Okay, close. Maybe you'll give it a try too.
So because the bitwise AND is comparing the very last one and then calling the method again, with the number shifted to the right, it's deleting the rightmost element. So it's comparing from right to left, and it's adding one. Whether it's adding one if the bitwise AND succeeds, which occurs when there's a one in the string.
Okay, good. Okay, good. All that is correct. So let me take my approach on walking through what this does. Right? This is a recursive function. Where's the base case? Yeah. Yeah, if x is just the number 0, return 0. That's it, right? You can decompose this into an if-else statement. So there's the base case. What's the recursive case? Yeah.
So if x is not 0,
If x is not 0, what will it do? It will return this value. And what is this value? This is the rightmost bit of x. That makes sense? Where did we see this in our programming assignments? PA3 part any to any, right? Something along those lines of converting bit representations. So this is examining the very last bit, right? It's just masking for the very last bit. And if it's 1, return 1. Plus, what else? Here's the recursive case. So it will call itself with what argument?
x, but right shifted 1 bit.
Yeah, so you eat 1 bit off of the right side, right? Right shifted by 1 bit. So all this way through, in other words, this will take this number, convert it to binary, and tally the number of bits that are 1. That makes sense. And so this is just a neat little recursion function implementation. And all of this is implemented very naturally using the stack discipline. So one exercise, if I had GDB fired up, is we can run this program and examine the stack, right? We can trace through the call. We would set a breakpoint at pcount_r and just see each time pcount_r is called itself. You can examine the arguments and also the shape of the stack as this is called. Now, here's a qualitative assessment. Is this a good way to implement count bits? If I just wanted to count the bits of a number, is this actually a good implementation? Why or why not? Yeah.
Could potentially have a stack overflow if you have a lot of digits.
So one proposal is maybe there will be a stack overflow. So good guess, that's a good proposal, but what's the deepest, do we really have that risk? So what's the deepest number of recursive calls we might encounter here?
64.
64, why 64?
Because that's like the maximum like number of bits in the bit string of like the binary of like whatever number you're putting in.
Yeah, sooner or later, right? Unsigned long, shifted rightward by 1 bit all the time. Sometime before 64 such shifts, x will be 0, and you exit the recursive call, right? So the call depth here is just 64. But still, what you say is good. Doing this recursively is kind of overkill to implement this function, which could be implemented as a loop, right? And so there are many situations in source code where a programmer naturally would write something that looks like recursion, but there's a certain kind of recursion that can be automatically converted into loops, right? The criteria here is kind of subtle, and this is just kind of added, kind of nice to know in this class. If your function is something called tail recursive, it can be automatically get converted into loops. And so what does it mean for something to be tail recursive? It means that as a function, the last evaluation is a recursive call to itself, right? So this shape here of this implementation, the last part of the assembly is a recursive call to itself. Therefore, pcount_r, the way it's written here, is tail recursive. And tail recursive functions can be rewritten to be a loop. Yeah.
Is it more efficient for it to be rewritten as a loop, or is it like less or equally efficient to keep it recursive?
So good question, right? What is the penalty of recursion? Right? I've spent the first half of the slides on what we have to do to support recursion. So what does the compiler have to do to write assembly to allow this recursion?
They have like overhead storage that you have to make for each time you iterate to like instantiate a new variable each time.
Yeah, right. So every time we call a function, we have to go through this whole discipline of saving the registers, building the argument stack, passing the argument into RDI here, calling the function does its work, come back, get the value from RAX, and so forth, and restore the register context, right? There's a lot of work to support function calls and recursion, and that's in contrast to if this were just a loop, right? What does it need to do to implement a loop? What does a loop look like in assembly, roughly speaking? Yeah. Just some jump statements, right? Okay, actually now I remember where the corresponding example is, right? It's going to be here. Loop C, here, count bits 4, right? This is exactly pcount. This is the same functionality as pcount_r, but just a loop, right? And we've seen what this looks like as assembly. It's just some jump statements, do a comparison. If your number is not yet 0, shift and loop again, right? This is a lot more efficient at the assembly level to do this as opposed to do recursion. But like I said, there are situations where it makes sense to program things as recursive. So for example, what's an example of something that very much makes sense for us to program as a recursive way? Yeah.
Think of like factorial.
No, that's like one of the worst examples, actually. Factorial. What else? Right, factorial, you can definitely, to calculate factorial, you could just write that as a loop. Right, so the other example of something like this could have been a recursive factorial calculation. But factorial, you could just write it as a loop, right? What programming assignments we did so far in this class where recursion is essential? Yeah. DFS, BFS, all these like graph traversal algorithms naturally use recursion, right? It's so much so to the extent that depth first traversal, the recursion, the stack of the DFS data structure, or the data structure needed to perform data structure, we directly piggyback off of the function call stack. So there are situations where we want to recurse, and so we want to take advantage of the compiler take advantage of automation to convert from recursion to iteration. So let me walk through that example right now. So here I am in assembly procedures. I have the code for 3recursion.c, and I will make 3recursion.c, do this compile. So this will invoke GCC with OG, so no optimizations, and furthermore, preserving assembly that looks like the original source code. And it will create the assembly code recursion.s. So let's go take a look at recursion.s here and look for the implementation of pcount. So there's pcount. Right, there's pcount. Let me try this again. Oh, okay, I see what's going on. And here we are in the right directory, that's right, good. Okay. Recursion S. Here, okay, good, recovered. So compiling with no optimizations, right? Pcount, the structure is exactly what we expect. Pcount has a recursive call to itself there. So pcount calls into pcount, right? There's a recursive implementation reflected in the assembly. Now, the compiler, you can direct it to optimize away tail calls, right? So this is enabled with a specific flag that optimizes away tail calls. And more generally, it's automatically included at higher levels of optimization, right? So if you turn on O2, so beyond the second level of optimization, it will optimize away this tail call. So let's implement that now, right? So instead of compiling with no optimization, I will enable O2, second level optimization, make again, and examine the source code again, look for pcount. So the label for pcount starts here, and already, so here in this pcount assembly implementation here, no more calls to itself, right? So what was originally recursive source code in the compiled version with O2, the recursion has been compiled away. Does this make sense? And why is that more efficient? Yeah.
Because you don't need to like push arguments and then pop them again for every recursive call, since you just have jump statements.
Good. So you can think of this even, so right, so just jump statements, just iteration. So you can think of this even in a more neater way, right? What's also happening here is kind of mind-blowing too. When you do this tail call optimization, in other words, instead of creating a new frame every time you recurse, the compiler is cleverly just using the same frame over and over again, right? You call into pcount and just one frame, replace that frame with a loop, and just reuse the memory space needed for just one level. Yeah.
So like the space complexity of the optimized one is definitely better, but what about the time complexity? Are they still around the same at this level, or is the optimized version actually faster?
Good question. So time complexity, at a complexity level, right, in terms of big O notation bounds, are they fundamentally different, expensive, different cost?
Like they're probably both like O n or something.
Both are ON.
But like when we go to like a microsecond level, you know, I wonder which one. Maybe if we have a really long number, will one start to edge out further?
You'll notice it, right? Because this is essentially a fixed constant faster, right? There's always a constant coefficient, and here it's the constant coefficient that matters of the loop implementation as opposed to the recursive implementation. Good. And just to tie into some further classes, right? One of the classes you may take is something called PrimProg, Principles of Programming, where you'll learn about what functional programming is. And functional programming has this very neat enforcement where in order to write correct functional program code, all of your recursions are automatically going to be tail recursive, right? So because they're all automatically tail recursive, compiled functional programs can automatically turn recursion always into iteration, right? These are kind of ways in which architecture considerations, is this loop or recursion implementation, feeds up into how software should be written to play well with the computer hardware. Okay, any questions about this slide so far? Yeah.
In more abstracted languages like, let's say Python, is there similar optimization of like recursion?
I mean, if you're in Python land, you have all other types of problems, right? You know, so that's a good question, right? So in studying C and Java, right? In C and Java, these are strongly typed languages. How are types enforced in C at the assembly level?
Well,
Everything has a strict definition. The compiler knows what data type it is, so it will use the right instruction size and move the right amount of data to and from memory to enforce types, right? And if your language has no types strongly enforced, such as Python, right? You don't have strict type enforcement. It means that every piece of information has to carry along with it some metadata on how you're supposed to process that data, right? That's already one big overhead that a weakly typed language has to pay. Another kind of just kind of filling in some details and neat information here, right? Why not automatically always include this optimization, right? When I first introduced these different levels of optimization, we got a question about why not always have really high power 04, 05, maximum optimization. Yeah.
I believe if you have like really long particular code, you don't want to like make changes to it, where you have to like
Right.
search for these subtle changes in a huge block of code usually.
Yeah, so a couple things to point out here, right? So performing this analysis for the compiler to identify, aha, this is tail recursive, I know how to compile it into iteration. It's a pretty costly compiler analysis optimization, and so it's not automatically enabled at 01, right? 01 optimization, you're still interested in rough and fast compilation, and as you crank up the optimization level, you're willing to pay more time. You're allowing to let the compiler run for longer, right? So only at higher levels of optimization is tail call optimization bundled in. Yeah.
So while things are being developed in-house, maybe developers use like the lowest optimization level of any, and then when it's released as like, you know, consumer software, it's like a very high optimization level.
Good point, right? So good discussion there. So when you're still developing programs, when the program is still under construction, oftentimes you would compile with -G, right? -G maintains all the debugging information where you can open GDB and see each assembly line of code corresponding to the original source code symbols, right? And as the program matures and you're about to push the program into production, then you don't want to bundle these debugging symbols and you want to enable high-level optimization for performance. That's exactly right. Okay, so couple of things to point out next. So what we need to talk about next is, so what's the whole point of phase 5 and phase 6? Right, so who's done phase 5? So what's the key thing to know about phase 5? Yeah. You're searching through an array, right? And so the key kind of lesson that phase 5 is illustrating is that in order to create arrays in assembly, it's basically an address calculation with an appropriate dereferencing. So for this example, we'll go to the example codes. So for assembly data, I have an example code on one arrays.c and its corresponding assembly code on the left side here. Okay, so I'll give you a quick moment to digest what this C source code is doing. And we'll start with just the nested array example here. Okay, so our task right now is to convince ourselves why get nested as assembly is implemented in this way. So task number 1, what's going to be in these registers here? I've got RDI, RSI, RDX. What do these registers correspond to? Yeah, just shout it out. Yep, an RSI, row index, RDX, call index. Good. Okay, so what we want to do is we need to return the access into the array, right? So why is it implementing it in this fashion? Let's trace through this line by line and see what's going to happen here. So what's the effect of this instruction here? LEAQ, RSI, RSI for RAX. What's going to get stored into RAX? Yeah.
So it'd be RSI plus RSI times 4. So I guess the number, like the bit offset from the array pointer.
Right, so it's going to become RSI plus RSI times 4. In other words, it's going to be 5 times RSI, and that's going to be stored in RAX. And what's RSI again?
The row number.
So row index, 5 times row index. Good. That makes sense. Right, next line of assembly. What will the next line of assembly do? Or maybe we need to pause here, right? What's the point of 5 times row index? What's the significance of multiplying by 5 here? Yeah.
That gets you like the pointer to the first element in your row, because like the first one, like first, because it's like times 4, I'm gonna say it's like
So think about this way. Yeah, or think about it this way, right? Suppose that my row index is 1. So how far into nested array should we read? Right? Every row is 5 digits. And so the way that these arrays are implemented is the 5 digits are just chained together, right? So I have a 2D array here, the first 5 digits for the first row, second 5 digits for the next row, last set of digits, the last row. And so if row index is 1, I have to jump across the first 5, right, and get to the second row for 0, 8, 9, 0, 1. That makes sense. Okay, next line of assembly. What will this do? What's going to be stored in RAX? Yeah.
So it's going to store 4 times the original RAX plus RDI.
Good. So good, but what is RAX at this point? Right, this has already updated RAX, the value of RAX here, so what is RAX at this point? Yeah, so it's 5 times row index, 4 times 5 times row index, plus what? What's the value of RDI? So the beginning of the array. This makes sense? So at this point, what is RAX concretely pointing at?
It points to the row that you're trying to get.
Yeah, right. So if row index is 1, now RAX is a pointer to this location right here, the beginning of row index 1. And it's accounted for the size of each row already, and it's accounted for the size of each digit in the number, right? It's accounted for the fact that each integer is 4 bytes. So this is why there's 5 times 4 into the row index. So next, what we have to do, what's the next step going to be? Right, I've accounted for row index, so logically it has to account for column index, and how is that going to take place?
As the column index that gets passed into the function multiplies it by 4, uses the ints, or 4 bytes each, and then adds it to the row that you're already on.
Good, right? That is implementing these semantics here of now I've accessed into the array, I've moved to the correct location for the row, and now I also have to move into the correct location for the column. Yeah.
If you had like 7 rows instead of 5, would the first LEA instruction have a 6 instead of 4?
So good question, right? So suppose that the zip code digits here are 7 digits per zip code. So how might that be reflected in the assembly here? Right? This is compiled code where the arrays are of fixed length already. So how might it implement 7 digits per row? Yeah. So it will have to pull off some more trickery, right? So to implement 7 digits per row, it would not be able to do that in one LEAQ call, right? There's a strict kind of constraint that these addressing mode calculations, this digit here, the multiplier, has to be a power of 2, right? Because the powers 2 reflect the size of data types. And 7, you can think of it as 6 plus 1. 6 is not a power of 2. It's 4 plus 3, but then 3 cannot be implemented in one go. So we will probably have to do it in 2 separate LEAQ calls to calculate 7 times the row index. Okay, so this makes sense. This is the implementation for getting nested arrays. Now, for the other version here, right, multi-level array, what's the difference in terms of syntax? That's different going on here. Yeah. So it's using a pointer, good. So there's a couple things to point out what's going on here. So nested array is declared as a contiguous block of memory, right? Here it's declared as I have an array which I want to be 3 rows times 5 columns. Now, multi-level array is constructed in this way here. Right, the multi-level array is constructed like this. Is there any guarantee that the whole multi-level array is going to be one contiguous block? No, right? And what might have been a change to how I structure this code to not necessarily guarantee that the array is one contiguous block? Yeah. These are pointers to individual arrays. Good, right? This is multi-level array is an array of 3 items. And what are the items? They are pointers to arrays, pointers to integers. And one way in which this might have been non-contiguous is I could have written the code in this way, right? Would this compile just fine? I just moved the line defining Piscataway's zip code to be above nested array. Right? This code compiles the same, but the layout of the local variables for this code is going to be different. Right? It's going to call into this function, and it will lay out its local variables of the stack in a slightly different order. Right? And so in order to access multi-level arrays, it's a slightly different calculation that's going on. And so let's study the correspondence between this and this here. So same exercise. What's in the registers? The same, right? RDI, RSI, RDX, all the same contents. What takes place after this move Q instruction? What gets stored into RAX? Yeah.
So 8 times the row index plus the array.
Right? That's good. And what's another key distinction that's going on here? This is a move Q instruction as opposed to LEAQ. Why? Right? Here we're actually dereferencing this location and putting that value to RAX. In other words, what's RAX storing at this moment? It's a pointer to where? Yeah. It's a pointer to the appropriate row, right? So suppose I wanted to get multi-level array first item, which is New Brunswick, and so it's a pointer to the first item of New Brunswick, right? This now is a pointer value that's being stored in RAX as opposed to just an index, which will be used later on. Yeah.
So like the multi-level array pointer itself, is that a pointer to? Actually, never mind.
We can revisit that. Yeah. So what's next? I've accounted for row index. What's the next step? Yeah, column index. So what's the outcome of this next line of assembly? What gets stored? Yeah.
The value at the column of that row.
The value of the column at that row, right? So this is going to be the dereference value of array plus 8 times the row index plus 4 times the call index. Right, so the subtle thing here is kind of in our pointers lab, when we started 211, we talked about how arrays and pointers are very similar in how they achieve their goals, but at the assembly level, they are a little bit different in terms of how they are manipulated to get the same effect, right? And this illustrates that exactly. So this exercise here, onearrays.c, it corresponds to the data slides from the textbook. They work through basically the same little example. There is an interesting coincidence, which is not super useful information. But the particular year that these slides were prepared for, so 2015. So that year at CMU was a very interesting year because 15213, which is the code for their 211 class, right, in 2015, happens to be the same zip code as where CMU is, which is a very strange coincidence, right? You can go look up where the zip code for 24211 is, and it's somewhere in Virginia. So yeah, anyway, the worked example, onearray.c, just corresponds to this set of slides here, illustrating the same idea. And this rolls into one of the important stepping stones for our next chapter in this course, right? This idea that data structures, such as two-dimensional arrays, are really just contiguous segments of memory, right? If anything you gather out of this example, onearrays.c and phase 5 of the BOM lab, is that arrays are just sequences of memory, right? And so this has implications on how to write code that efficiently accesses the memory. Good. So there's one kind of in the 7 minutes left. One useful thing that we should do is for the BOM lab, let's do a little bit of a tutorial or kind of work exercise on how to print the needed information for phase 5, phase 6, right? And so this is kind of to illustrate, to tie things together, right? So if you work through phase 5, phase 6, but kind of missed these things that you need to know on like what's actually being taught in it, I'm going to point it out here, right? So let's set up my BOM environment. So break at explode BOM, break at phase 6, layout next. I want my register and my assembly side by side, run my solution. So this has been worked through phase 6. And we're gonna just step through here. It's gonna read in the 6 numbers for my solution. It's gonna go through a nested loop, right? So you can visually see that there's a loop going on here. There's a nested loop checking your digits against some criteria. And where I'm trying to fast forward to is to the entry point where I see a data structure. Come on. Okay, I think we moved past that part now. Here, okay, good. So this is where I wanted to fast forward to actually see. Here is an assembly line of code for accessing a data structure. It's performing a memory address calculation and putting it into RDX. So if we wanted to inspect what's at this address, what will we do? Yeah.
So once we reach that thing, we do x slash x slash 5 plus 5.
Not
Right.
yet.
So there, right? It says that the label for this piece of memory is the label is node 1, and so here is some information at node 1. What's a way I can get more to print out? Yeah. So I want to get more lines. So same. So here is printing out 16 such entries now. And we need to see some structure here, right? What's a pattern that we should notice here? Right, so if you take a look at the help printout for the X command, one thing that you can learn is, in addition to changing how it's printed out, you can change its assumption on how many bytes are grouped into each data type by changing these parameters called the size letters. Why does it have to do this? You know, why does this have to be manually provided? Yeah.
Because there isn't really a division between these like different types of data. It's just kind of depending on what the user is requesting, because otherwise it's just a string of numbers.
Good, right? This is really just a string of numbers. GDB reading into the memory locations and printing out the memory locations, it has no idea how it should group the chunks of memory into meaningful numbers, right? So you have to kind of play around with how we do this grouping to get it to lay out the information in a meaningful way, right? So let's try 0x16G for giant, meaning 8 bytes, to see pointers, and as a hexadecimal at that location of 0x555555559220. Right, so here we see the linked list. Right, phase 6 is all about this linked list. What is the linked list? Well, the linked list has 2 fields. Here's one field, here's another field, and what is this? Yeah. Pointer to next, right? Here is the pointer to the next, and you can see how these are basically creating the linked list. There's 55520 at node 1, it points to 230, node 2, and so forth. Where does this last one go? Goes to another node, right? So you have to go look for that node. So GX, same. We'll go chase down that node 5, 0x 5555 5555 9110, and there is node 6, right? It wasn't stored contiguously with the rest of the nodes. Why not? What's the complication here? Yeah. Is it just because it's the end of the linked list? So node 1, 2, 3, 4, 5 are put together there already in the local variables, right? This is the local variable segment of phase 6. How come, why is node 6 hanging out at some other location, not contiguous? Well, in our example, I just showed you a way to do that, right? The local variables are laid out according to how you organize your source code. And this code here, where Piscataway is written at some other piece of memory, has the same semantics as this, right? So you can visualize why is node 6, the 6th node of the linked list, hanging out somewhere else in the code. It just got moved to somewhere else, just like this. Okay, so that wraps up a little bit of the data stuff, and we'll come back on Thursday to talk about caches.
Question about the submission file. So like this is what's in my tar file.